Okay, let's start. So today we will review some very basic concepts of the analytical mechanics first. That is, the first is configuration space. That's an abstract space that is very different from the physical space in the Newtonian mechanics. And in configuration space, the coordinate is called the generalized coordinate. That is Q or Qt. It is a function of time. And this is a generalized coordinates, right? And it could be the same as the position of the physical space, but it need not to be exactly the same. Sometimes it's the same, but most of the cases it's not the same. Okay? And even sometimes, that the dimension of the generalized coordinate could not be the same as that of the positions in physical space. Okay, so we have d-dimensional space of the configuration space. That's a dimensional. That means we have the QA, and A is equal to 1, 2, ... and D, like this. And in the configuration space, we have the mechanics that is called the Lagrangian mechanics. Lagrangian mechanics. That's the first analytical mechanics that we have met, right? In analytical mechanics. And in analytical mechanics, we have the principle of the least action. That is the first step of deducing some equations of the motions, right? The principle of the least action is also called the Hamilton's principle. So that is that delta S is equal to 0. That means that the value of the action should take the extreme values to make the stationary value of that. And then you got the actual physical path. Okay? And so, as the action is defined as this, as the integral of the Lagrangian. Okay, and from this principle, we can get a dynamical equation of the Lagrangian mechanics. What's that? Remember? That is called the Euler-Lagrange equations, right? Euler's Lagrange equation. What's that? Still remember? The Euler-Lagrange equation is that d over dt partial L partial Q A dot is equal to partial L partial QA. Actually, partial L partial QA dot is the same as the canonical momentum later in Hamiltonian mechanics. Remember? Yes, good. And how many A do you have? You have D choices of the D of the equation. So altogether you have D equations. Now the equation is the second order partial differential equation. Right? You have D, altogether D equations. That is the second order differential equations. So that's all for the Lagrangian mechanics. So you may ask, does any relations between Lagrangian mechanics with the quantum mechanics in the future? My answer is yes, but not now. Maybe not in this course, but I can give you a very brief preliminary discussions of, oh, it's too long, I think it's not too good. Well, from Lagrange mechanics, you can get a concept of the path integral and Lagrangian based quantum mechanics and quantum field theory, especially the quantum gauge field theory for the quantizations of the interactions between the fields in the future. And for the interaction systems, if you want to quantize some interaction Hamiltonian, you must use the Lagrangian mechanics. You must use the path integral. You cannot do that by the a canonical quantization procedure. No, you cannot. So Lagrangian mechanics is very, very important and very fundamental for the relativistic quantum mechanics in the future. So this normally we have the non and relativistic and relativistic. That's both valid. But for the non-relativistic case, we prefer not to use the Lagrangian mechanics. We prefer to use the Hamilton mechanics. Okay? That's a very conceptual introduction to you guys. This path integral was very originally introduced by Paul Dirac, but later it was accomplished by Richard Feynman. Okay? Dirac and then Feynman. Okay, so that's a very brief introduction of the Lagrangian mechanics. And now, you're paying more attention about the Hamiltonian mechanics now. So first, we'll change from the configuration space to the phase space. The phase space, we have another thing that is called the canonical coordinates. Canonical coordinate. What's that? What's a canonical coordinates? The numbers of the coordinates in phase space is doubled than the configuring space. We have one that is QA, that is kept from configuration space. And another one is PA, that is called the canonical momentum. And this is called the generalized coordinate. This is also called the canonical coordinate or positions. And this guy is called the canonical momentum. And also it is called the conjugate variable of the generalized positions. Okay, so it has many names, the same. Canonical momentum, the conjugate variable of the generalized coordinate, and so on. Okay, so altogether you have 2D dimensional space. Okay, and how to transform from the configuration space to the phase space? You need to have a very important transformation or transform that is called the Loranda transformations. Loranda transformation, and Loranda is a very famous French guy. He's very famous in mathematics, and at least we have two important things from him. One is the Loranda transformation that is very frequently used in the analytical mechanics and also in thermodynamics. And also, I think you guys should be very familiar, or maybe you have the knowledge of the Lorentz polynomial, right? You have the spherical harmonics if you have learned the quantum mechanics at the undergraduate level, or you have learned the classical electrodynamics before. You have the Lorentz function, Lorentz polynomial. Remember that? No? Lorentz is like this. This is Lorentz function, Lorentz polynomials. It's very, very important. If you have times e to the im phi, and this function is called the spherical harmonics, and this is very important for us in this semester because we have the angular momentum, and angular momentum is it's very much tightly connected with this function. So, and this is connected. This is connected Lorentz function, Lorentz polynomial. If in this function, in this polynomial, if it is a phi independent, you will not have the m index here, and then it is called the Lorentz polynomial. Okay, remember? Yes. So this guy is very important, and this is also a very nice guy. Okay, and what is Lorentz transformations? Lorentz transformation is like this. The definition of the momentum here is defined as the partial L partial Q A dot. And then you will have another Q P T. This is called the Hamiltonian. This is called the Hamiltonian. And this guy is the key thing in Hamiltonian mechanics. It is equal to the P A Q A dot minus L Q dot P. Okay? And I would like to remind you that this function is the key. This function is the key in Hamiltonian mechanics. But what's that? We have learned the Lagrangian function. We have learned the Hamiltonian function. But what is that? And maybe you can say that, okay, Lagrangian is very simple. It is the T minus V. That is the subtraction of the kinetic energy to the potential energy. That's just a very special case, but it is very frequently used case. And in this case, the Hamiltonian can be written as the T plus V. That is the addition of the kinetic energy and the potential energy. But that's only a very special case for the Hamiltonian and for the Lagrangian. So that's what I want to remind you of that. Okay, we have the phase space now. We have 2 dimensions. We have more dimensions than before. And so the equation, it looks simpler than the Euler-Lagrange equation. And situation is yes, because we use the same principle that is called the Hamilton's principle. That is called the principle of least action, whatever, the same. But now the action is defined as the same. It's still the Lagrangian, but what is Lagrangian? Lagrangian now is equal to this guy minus the Hamiltonian. Okay? So minus Q P T dt. Okay. So now the action is defined in this way. And this is equivalent to this. And we use the same principle. That principle is called the variation principle, the principle of least action, or the Hamilton's principle, whatever, many names. Or maybe if you like, you can say that now that the name of that principle is called the Fermat principle. Okay, it's good. And Marcus principle, okay, it has so many names. If you like, if you have interest, you can just go to the wiki or some other very fruitful websites. You can learn a lot of knowledge of the variational principle in different types, in different ways, and but describe the same thing. Okay. And from this, we got what's the name of that equation for the dynamic behaviors of the particle systems? From this, it is called what? Hamilton's canonical equation of motion, right? Yes. Hamilton's canonical equations of motion. Okay. And what's that? Remember that? That equation is very, very, very simple. Much simpler than this one. It looks much simpler. That is a QA dot is equal to partial H, partial PA, and PA dot is equal to minus partial H, partial QA dot. So that is the canonical equation of motion, right? Remember? Yes, good, because that's only last time we just derived the equations step by step. And after that, we can have a generalized form for the canonical equations of motion. What is the generalized form of that? And that's very special for the Hamilton mechanics. That's very different from the Lagrange mechanics. What's that? Because in Lagrange mechanics, you can just get the equations of motions, of course. But in Hamiltonian mechanics, you can get any arbitrary function that's a function of the canonical coordinates. And you can get the dynamic behavior of that arbitrary function. Remember? So that is for any f. F is any dynamical function of this. It is a function of the q and p and t, right? So it's a function of the canonical coordinates. So, what's that? What happens? Yeah, it's very important. So df dt, df over dt, so that is the dynamical behavior of the function f, right? It is equal to partial f partial t. It is time-dependent explicitly function of t. If it is not a time-explicitly time-dependent function, you will not have this term. Okay? Plus what? Plus this. Plus this. Then that is called, this bracket is called the Poissonian bracket. Or we call it the classical canonical commutation, right? Remember that name? A, B. The Poissonian bracket of A, B is defined as this. Partial A, partial QA, partial B, partial minus partial A, partial PA, and partial B, partial QA. So that is the definition of the Poissonian bracket. Or we call it classical canonical commutation. And this bracket is called the commutator. It's a commutator, okay? So because it is very interesting, CCC, classical canonical commutator. And in quantum mechanics, we have another guy, which is very similar to this. It is called the quantum canonical commutator, and it is simplified as a commutator or commutation, right? But you should remember, you should keep in mind that the commutator is canonical. You must have canonical variable, and then you can make the commutation calculations. Otherwise, you cannot do that. Okay? So it must be based the canonical coordinate. If you have the two functions, you have the commutator of the two functions. The two functions must be the function of the canonical coordinates. If it is not, don't do that. You cannot do that. Okay? Keep in mind, that's very important. And from this, we have the Hamiltons. This is Lagrange mechanics, and this now is Hamiltonian mechanics. Okay, we have this. From the Hamiltonian mechanics, you can get, correspondingly, you can get what? You can get the Hamiltonian based. But normally, we do not say that because it is the default. It is a default. The quantum mechanics, for the very beginning, that it is based on Hamiltonian. So everybody knows that it is based on the Hamiltonian, so we can just, okay, and this is the quantum mechanics. But keep in mind that this quantum mechanics should be non-relativistic. Okay, so that is a non-relativistic. This is very important. It is only valid for the non-relativistic case. For the relativistic case, it's not the same. It's not be valid. Okay, so I think that I have given a very brief introductions and summarizations of what you have learned about the Lagrange mechanics and the Hamiltonian mechanics. Have all of you guys have understood what I've told you? Any problems? If you have problems, please raise your hand and you can ask the question now. Or maybe you can, if the question is too complicated, you can just write down and then send email to us. And then we can discuss about that. Okay? Okay, good. You're so smart. Smart guy. Now, let's discuss another thing. That is the key. One of the key and the core of the quantum mechanics. And it is also originated from the classical mechanics, Hamiltonian mechanics. And I think that you guys have, maybe you have noticed that we have a term that is very frequently used. That is called canonical. Canonical, what's the meaning of canonical, right? So we have, I have a canonical. So this term means, for the simplification, it just means right. And in Chinese, I think that the Chinese translation of the canonical is very good. It's like this. You can just think that it is something like this. But anyway, it's right. It's all right. It's definitely right. It is absolutely right. Something like this. So that's a canonical. So the first thing that we have met in canonical term, that is canonical coordinate, right? Well, canonical coordinates, so you should keep in mind that in classical mechanics and also in quantum mechanics in the future, every physical quantity or observable is canonical. You have the position operators, you have the momentum operators in the future in quantum mechanics. It should be canonical position and canonical momentum. You cannot use the kinetic momentum in the future. And this is very, very crucial for the charged particles in the electromagnetic field. In other cases, the physical and canonical is the same. But for the charged particles in electromagnetic field, it's not the same. The kinetic momentum is not the same as the canonical momentum. That's very important. You should keep in mind that's a very, very serious problem. Okay, what's the second thing? Canonical what? The canonical equations. The canonical equations means the Hamiltonian canonical equation of motion. And this equation we have, this is the canonical equation like this, a Q dot and P dot, right? And from this equation, we have generalizations for this. And this is called the generalized canonical equation of motion for any kinds of functions of the Q and P. And then from that, you got the very, very important operation that is called the Poissonian commutation, right? And this bracket is called the Poissonian commutator. And this operation is called the canonical or Poissonian commutation, right? So we have already had the term of commutations. So this term is not originated from quantum mechanics. It's from the classical mechanics. And canonical from classical mechanics. Coordinates, canonical coordinates from classical mechanics. Equation, classical mechanics. Commutator and commutation, classical mechanics. That's not the quantum mechanics. And a very important guy here is the canonical transformation. I will teach you this. This is a little bit more sophisticated, so I need to have another 15 minutes or something to teach. So it takes time. Okay, so we have so many canonical things. We have so many very, very crucial, very important concepts. And we know that from this, we have the Q, A, T, that is one of the coordinate of the canonical coordinate, and P, A, T is equal to this. And this is a very typical operations in the Lorentz transformations. An equation, QA dot is equal to partial H, partial PA, and PA dot is equal to minus partial H, partial QA. And for commutator, you have the A and B, PB is equal to this. I would like to write it again to make you guys realize that it's so important that we should be very familiar with that concept. Okay. And this guy is more sophisticated. We have the Q t and its function, that is called the Hamiltonian, will transform to another guy that is called the Hamiltonian. That means the new Hamiltonian. Okay? Some guys call this guy as the Hamiltonian because it is a new Hamiltonian. It's very interesting. And now the canonical coordinates of the Q and P will be changed to the capital Q and capital P, like this. So everything has been changed. The coordinates and the Hamiltonian has been changed. But what is kept invariant? You know, after this transformation, CT, canonical transformations, you have one thing, very important thing, is kept invariant. What? Commutation relation. That means the Q, P, if you have the if you use the Q and P to do these calculations of the Poissonian bracket, will be the same as the Q and P in the new coordinate. That is kept invariant. So, generally speaking, every canonical commutation relations of any canonical coordinates or functions will be kept invariant after the canonical transformations. So the equations of motion will be kept invariant. So if you have the canonical thing after canonical transformation, everything will not be changed. So that's why it is called canonical. And that's right. Right coordinate after right transformations, you got the right answer because that answer is always the truth. Understand? So that is why it is called canonical. So now, I also want to mention one thing, that this guy, if you generalized from classical mechanics to the quantum mechanics, what you get is AB will be changed to AB like this. So all of the changes from classical mechanics to the quantum mechanics is only this. The Poissonian bracket, the classical canonical commutation relations will be changed to the quantum canonical commutation, and that is a commutator here. And every function here will be changed to the operator. You have the hat A and hat B. That's only the difference between the classical and quantum. All of the classical canonical commutation relations you have got in the classical mechanics can be shifted to quantum mechanics by only insert such a constant 1 over IH bar. That's all. And you just change every A or B or something into A hat, B hat or something. Everything will be the same as the classical mechanics. So quantum mechanics is not something that is you got suddenly. If you have such a feeling, that's only because that you are not so familiar with the classical mechanics. Okay. And one thing left that I want to teach you what is the Lorentz transformation. Lorentz transformation is important in analytical mechanics and also in thermodynamics. So I would like to mention here. And if you want to change the function of x, and that is f, it is a function of x. If you want to change to another variable argument, you may change to GP. GP is another thing. That's a function. And it is equal to the fx minus the x times the fx prime. So this is called the Ⅲ transformations. It's very simple. It's just, this is the Ⅲ transformation. You may ask, what's the meaning of Ⅲ transformations? What's the advantage of that? The advantage of the Ⅲ transformation is you do not like the variable x. You prefer to use another variable. And what's that variable? That's p. P is equal to this. If you make such a derivative, you got the p, that's a new variable. And after this, if you have the fx minus x f prime, you got a new function that's a function of p. And p is equal to the derivative of the older variable x. And then after that, after this transformation, the fx function has been changed to another variable, gp. You do not have any, you do not have anything related to x. That's just an advantage of that. And also you can generalize from a single variable to multivariable. In the Ⅲ transformations, you can generalize to, if you have the fx, something I and y, j or something, and then you can change to a g. xi is kept invariant. You want to change to pj, and that is the fx I yi minus, oh, this is j. J, well, you have, you do not like to have the y, and all of the y has been changed to the p. And p, what is p? P is the partial f, partial y, j, and you times yj. And after this, you will not have any yj left in a new function. You can just check, you can verify this. This is a very simple transformations, but it's very useful in the future. And sometimes we use this definition of the transformations. This definition has been frequently used in the thermodynamics and in the canonical transformations later. I will teach you later. But in the transformation from configuration space to the phase space, we have an opposite sign. You notice that, right? That is, this is p q dot minus f. So that is the definition over there. So we have different kinds of the applications of Ⅲ transformations. Okay? Confused? Maybe? I hope that you have understood what I've told you. Okay, we can take a break. Now, canonical transformation. What is a canonical transformation? That is the right transformation. CT. So abbreviated as the CT. Okay. I have asked you a question. How many Hamiltonian or Lagrangian can you have for the same system? The same equation, same Euler-Lagrange equation, or the same Hamilton's canonical equation of motion. One equation corresponds to one Hamiltonian or one Lagrangian? No? What's your idea? I can show you how many you can have. remember that what is the principle of least action? What is Hamilton's principle? That is this. Right, right? And what is the definition of S? It is this. T1, T2, I have the delta, LQ, Q dot T dt, right? Suppose that if you have plus if you have such a function that is the total differential, what's that? So this integral should be gt, right? And delta g t1 is equal to 0 and delta g t2. Because t1, t2 are the two endpoints. So no variation in the two endpoints because the two endpoints are fixed. So you don't have any variation of that. Remember? What's the meaning of variation? What's the meaning of difference? What's the meaning of differential? You got? Okay, so no variation here. Not only dq t1 is equal to dq t2 is equal to 0, but also for any function of the t1 t2, they do not have any variation. So the variation of the gt1 and gt2 should be equal to 0 because the t1, t2 points are fixed. Okay? You got? Yes. If you do not, let's discuss later after class. Okay? I can give you more demonstrations for that. So if you have such a function, you add such a thing that no change. So what does it mean? That means if you have L Q dot T dt, oh no, sorry. Yes. Okay, I think that it's just, we just use this. So now let's take a look at what is L. The L is equal to this PA QA dot minus Q dot T, right? And now if you have some new coordinates in the phase space, that's the new coordinate and new phase space, you can write down like this. PA QA dot, right? Minus K Q P T, right? Any problems? You can write it down like this. And to make that, okay? Oh, I'm sorry. It should be like this. Okay? And plus one thing. This is using the old Hamiltonian, and this is using the new Hamiltonian. And of course, if you add some new thing, that is dg. And then you got no change. no change. That's the same thing, because we have analyzed from this, right? So the new and the old Hamiltonian should have the following relations. That is PA dQA minus H dt is equal to PA dQA minus K dt plus, you can write like this. And this is a very important basic equations that we want to derive for the following derivations for the canonical transformations. And this is the old canonical coordinate. And this are the new canonical coordinate. And this is the old Hamiltonian. And this is the new okay. So now we have the old coordinate and old Hamiltonian and the new coordinates and old Hamiltonian. And what's this? This guy, the function g, is called the generating function. Now, it is called the generating function. In Chinese, it's like this. And this guy is very important. It is important not only in the canonical transformation, but also in the conservation law for the quantities. Okay? So, and now the question arises, what's that g? What's that g? Do you have any relations between the g and the old and new coordinate? Can you derive the relations of that? The answer is yes. And how many choices do you have for the generating functions? In principle, you have infinite choices. And from this very beginning, from this, you can see that the Lagrangian has so many choices. How many? Infinite choices. It could be the t minus v, of course, and t minus v plus g. It's okay if that dg is, it's a total differential, and that works, right? So we have you have infinite choices of the generation functions, and then so you can have infinite choices of the Lagrangian and infinite choices of the Hamiltonian, of course. So do you like to have the infinite choices of that? No, of course. You prefer to adopt the most simple thing, right? So t minus v, the L is equal to t minus v together with h is equal to t plus v, is the simplest choice, and that we should adopt. We prefer to use this. We do not like to have something like that. But sometimes we may need to generalize this. We need to have some g included in the definition of the L or the h, and then to make the question simpler. If you face up such cases, you can do that. But normally, we adopt this. But what is the condition for these expressions to be valid? Do you know that? I can mention that there is a very brief condition to make these expressions to be valid. That is, when you have the partial L, partial Qi, partial Qj, you know that this is because you have the index of the I and j, so it is what? Matrix, right? And this is the determinant of the matrix. If this guy is not equal to 0, it works. So this is a very important criterion. It's called a high sign. You know Jacobian? Do you know that? Jacobian. High sign is this. And what is J? J is Jacobian. If you have a determinant that is called Jacobian, and the gradient of that is called the high sign. If you have that conditions, you can choose this. Otherwise, you cannot. So when this is valid, it is called the Lagrangian is a regular Lagrangian. If it's not hold, it doesn't hold, it is called irregular. So, but normally, all of the Lagrangian we face is regular. So we are very lucky for that. I can tell a very interesting story. Jacobian is the professor, and this guy is his student. So these two determinants are very important. So the student is the gradient of the supervisor. Okay? Okay, this guy. So high sign is a matrix, is a determinant, and Jacobian is a matrix and also a determinant. And this determinant has the relations of the gradient, and this is very important. And this guy is the criterion for the validity of the Lagrangian to be regular. Like this. Okay, so we can go further now. Okay, so this is just a very small note for that. But the important thing is that we want to know the relation of G with what? With the old guy, QP, and the new guy, capital Q and capital P. Okay? Okay, you got what the motivation of what we will do next. You got? Okay, good. So now the first question is, what is the function of G to be? Is the function of Q and P and capital Q and capital P altogether? What's your choice if you would like to simplify the problem? The G could be the functions of the Q, P, and Q, capital Q and capital P, right? But this is very general. We can simplify this. We can have 4 choices to make the problems much simpler. You know that we have only 2D equations. We have these equations for the Q dot and P dot. So altogether we have 2D equations. But now you have doubled. You have 4D equations. You have a capital Q and capital Q dot and capital P dot. So do you need that? No, you only need to have the 2D equation. So every time you can just change, the G to have the 4 choices. The first one is the Q kept the same, not changed. And then I just change the P to the capital Q. So this is called the first type of generating function. Okay, type 1. generating function. This is called the generating function for the first kind or first type. And also we have the other three choices, right? That's very simple. And then you can keep the Q invariant unchanged. And you can change from capital Q to capital P, right? Okay. And then you can change from this to this. You can keep the Q unchanged, but change this, small p, right? And also you have the G4, that is, you can change both. So Q, you can change from the small q to P and P. So that is the type, the second generating function, and type the 3 generating function, type 4 generating function. So you can have 4 choices. Every time you only change one variable, right? Originally, you have the Q, P, and you change the P into the capital Q. And then you may also choose the Q is kept unchanged and then change to capital P. And you can change the Q unchanged from this. And this is the basis. This is the basis. Because if you want to change from one to another, what tool can you use? That is the Ⅲ transformation. I have told you in last lesson that for Ⅲ transformation, you just change the variable, right? That's a way of changing the variables. So here is the P and capital Q, and this is the P and the capital P. So you have 4 choices. Altogether, you have 4 choices to make the canonical transformations to work. Got my point? Okay, and now I would like to show you how to get the first kind or the type 1 generating function. So now let's do that. PA dQA minus H dt minus capital P d capital QA minus K dt. You must know that the H is the function of the Q and P, and the K is the function of the capital Q and capital P. Now, you should be very, very clear. You should keep in mind all of the functions dependence of the variables. Okay? But you cannot, if you write all the things, it's very complicated. So I just omit that. And what's that? That is dG1. What is dG1? It is the function of Q and capital Q and T. And what's this? What's this? What's this? How to calculate the differential of G1? How to calculate? It should be like this. Partial G1, partial T dt, right? This is one of the terms. And plus what? Because it is also the function of Q, so you should have the partial derivative of Q. And also it is a function of capital Q, so it should be the partial derivative of the capital Q, right? So you also have this. So that is a partial G1, partial QA, and dQA, plus partial G1, partial capital QA and d capital QA. Any problems? No problem? Okay, now we can just compare each terms. I need to have some other colors that's and this guy and this guy and this guy, they are the dt term, right? So for the dt term, what can you get? What can you get for the dt term? So that is a k minus h is equal to partial g1 partial t, right? So you have, this is the new Hamiltonian should be equal to h plus partial g1 partial t. And something more. And how about the dq term? This is PA and partial G, partial QA. So PA is equal to partial G1 partial QA. So that is the relation between the generating functions with that of the canonical coordinates. Okay? And d capital QA, right? The capital QA here, you have the minus capital PA. And here, you have this. So you got the PA, capital PA is equal to minus partial G1 partial QA, right? Keep in mind that these relations are very important. So that is the relation between the generating functions with the old or new canonical coordinate, including the positions and the momentum. That's a starting point that we can calculate further. Okay, and from this, what can we get? We can get that the partial PA partial QB is equal to partial square G1 partial QB partial QA. Right? Okay? And from this, you can have the partial capital PA partial QB is equal to minus partial square G1 partial QB and partial QA. Right? And what can you get? You can find that the partial capital PB partial QA, if you exchange the index of A and B, you get it is equal to the minus partial square G1 partial QB and partial QA. So what can you see from that? The same, except the sign here, right? So you can get that partial PA partial QB is equal to minus partial PB partial QB. So you can find the relations between the new and old coordinates. You have all of the canonical coordinates here for the new and old coordinates. This is the old, right? This is the old momentum. What? Oh, this is the. Yeah, I'm sorry. Thank you. Right. You should be very careful about this calculation because the indices here are very, very easy to be confused. But the here, and also you can check. It's very interesting. P, Q, A, A, P, Q, B, B, right? You get the same things, and you can have the 4 relations between all of the canonical coordinates for both the new system and the older system. You can have 4 equations like this. And from all of these relations, you can derive that the A, B, which is the function of the Q and P, or the capital Q or capital P, and its positioning bracket for the QP. So this is in the old system, right? Is equal to AB QP. You can prove this. So that means the canonical transformations can keep the positioning commutator unchanged. So right transformations give the right answer. So that's kept always invariant. So that could be the right. So that's why it's so important that we have the canonical transformations. That's only the type 1 generating functions. And you may ask how to derive the second, the third, and the fourth generating function by Lagrangian transformations. G2, because what is G2? G2 is here. The Q is kept unchanged. And you have the, from the capital Q to capital P, right? So it should be G1, Q, and Q minus what? Minus QA partial G1 partial QA. Right? So that is the Lorentz transformations. And what is partial G1 partial QA? It's here. So it is equal to G1 plus A, Q, A, and PA. Right? And then so you can derive that the G1 is equal to G2 minus A, Q, A, PA. After that, you can write down dG1 is equal to partial G2 partial T dt. Of course, that it is a function of T. And also partial G1 partial G2. It is QA dQA plus partial G2, and it is a function of what? Of Q. Partial QA dQA. Right? So this term dG1 is equal to dG2 and minus PA, the capital PA dQA plus QA dPA. And then you can compare all these terms with the left-hand side of the equation. So you can get the similar equations for this. You don't need to just hurry up with just making the notes. We have the lecture notes, and we have the tables, and with all of the 4 types of generating functions, the result is just over there. So now you just need to get exactly my points. And then you should calculate step by step after the class. I can just show you the first type 1 generating function, how to get there, how to get these relations, and how to get this. And how to, from this, we can get these relations, canonical transformations, keep everything unchanged except Q, P, and H. Of course, the coordinates have been changed, the Hamiltonian has been changed, but the canonical equation of motion has not been changed. It keeps invariant. The Poissonian commutator keeps invariant. So that's why. Actually, when you have the invariant commutator relation, that means the canonical equation of motion is invariant, because the Poissonian commutator just determines the behaviors of the equation of motion, right? So once this is kept invariant, nothing changed. Nothing changed. But the only thing that changed is only the form of the Hamiltonian and the form of Q and P. But it doesn't matter. All the things changed makes the canonical things, canonical commutator, unchanged. So that's a very important key point of that. Okay. Yes, I think that maybe you just take the pictures of all of the canonical transformations, and then we can go further. Okay, let's come back, and then we have two things left. One is we have discussed about the transformations for the phase space, and now we want to know something about the dynamical behaviors of the systems. So we need to know some dynamical or the dynamics in the phase space. Dynamics. In phase space. I think that's important. It's important because that we have a concept of the phase space and the points in the phase space. It's very important because in the phase space we have the new concept that is called the state. In the phase space, we have the point which is called the phase point. What is a phase point? The phase point is QP coordinate. That's a point. If you have a phase space that is Q and that is P, you have a point here, and that is a point. That is a point in the phase space. And maybe you have some trajectories of the systems like this, right? And all of the points in this curve means that the dynamical behaviors of the points in a phase space. And this point is called the phase point. Okay. And the phase point can be used to describe the system's behaviors. And also we can have another function which is called the phase point density function. Phase point density distribution function. Which is called it is a rho, and it is a Q, P, T, of course. And of course the Q and P are the T dependent functions. And normally we can describe all of the particles in such a system because this space is an abstract space. And so all the particles in the phase space will not be annihilated or created. And so the probability of the particles in the phase space will be kept unchanged. So you can find that this guy, Q, P, T, if you have the d dimension of Q and d dimension of the P, you have the 2D dimensional phase space. And this integral, that means all the particles, or the probabilities finding the particles in such a phase space will be kept unchanged. And that is the Weyl theorem. That is sometimes we call the Weyl equation. That is the d rho over dt is equal to 0. And from this we can derive partial rho partial t is equal to the Hamiltonian commute with the rho for the Poissonian bracket. So that is the classical canonical commutator. So this equation is the Weyl equations. Normally we use this. And from this, because we said that from classical mechanics to the quantum mechanics, you just change AB to 1 over IH bar, and you have the head for the two operators A and B, and that you do not have any subscript here, because this guy is the quantum commutator, and this guy is the CCC, the classical canonical commutator, or Poissonian commutator. Okay? So from this, you can derive a very famous equation in quantum mechanics and quantum statistical physics. That is partial rho partial t is equal to 1 over IH bar H rho is commutator. And this equation is called the quantum Weyl equation, or sometimes we call it as density operator or density matrix equation, or we can call it as the von Neumann equation, or sometimes if you in Russian or in Soviet Union it is called the Landau equation, one of the Landau equations. So its equation is so important that it has so many names. And it is very frequently used in the quantum statistical mechanics. Especially, it is valid for the case of the closed system. This equation is only valid for closed system. But it is valid for both the pure state and mixed state. It is much more general than Schrödinger equation. Schrödinger equation is only a special case for this equation, right? Schrödinger equation is only valid for the pure state, but the low Weyl equation is valid for both the pure state and also the mixed state. That's very important. And this equation can be generalized from the classical low Weyl equations by this correspondence principle from the Poissonian bracket to the 1 over AH bar with the quantum commutator. From this way, you can just generalize from the classical to quantum equation. So classical equation, classical mechanics is so important. Now, classical mechanics has already prepared all of the stuff that you need in quantum mechanics, and even the results you have in quantum mechanics In quantum mechanics, you got nothing new. You just found so many things that are so familiar with in classical mechanics. Okay, so if you're not familiar with classical mechanics, that's already a pity. Okay, good. And now I want to introduce a concept of what? Of the divergence in space. Everybody knows that for the flow, you have the continuity equation, right? The continuity equation. And that is an equation for the conservation for the fluid flow. That is something like this. That's for the fluid flow. And that is in the physical space. And now we want to introduce another divergence, the divergence in the phase space. And in phase space, we can have this like what? We can define the fluid flow in the phase space like this. It is rho v, right? So it is the rho or the q dot. And that is the axis of the q. And also you have the axis of p. So you have the rho p dot, right? You have a two-dimensional space. That's a very simplified version for the divergence in the phase space. But you can imagine that what I mean. Yes? Yes? Oh, okay. I hope you so. Okay, and so what is the divergence here? What is divergence? It should be equal to the partial q, right? That's rho q dot plus partial p, rho p dot. Okay. Of course, you have this index like this, right? So that is the divergence of the current, the flow in a phase space. Yes? So let's calculate it now. Let's see what will happen for the divergence. It is the partial qa rho qa dot plus partial pa rho pa dot, right? It's very interesting. And you can get partial rho partial qa dot plus rho partial qa dot partial qa plus partial rho partial pa and pa dot plus rho partial pa dot partial pa. It is like this. So now we can just partial rho partial qa, and what's this? This is partial h partial pa, right? Yes? And this guy is rho. This is qa dot is equal to the partial h partial pa. So you got the second order derivative of Hamiltonian, that is qa and what? Pa, right? And this guy, partial rho partial pa, and this guy is equal to the minus partial h partial qa, right? And how about this guy? This is also minus rho partial square h partial pa partial qa. So what's that? You can see from this term and this term. And so the two terms canceled out, right? Okay, so what's that? So this is partial rho partial qa partial H partial PA minus partial rho partial PA partial H partial QA. And this is equal to rho H PB. So that is the Poissonian bracket of the rho and the Hamiltonian. Okay, good. So you can have the partial rho partial T plus yes, partial rho partial T plus this is equal to 0. And so you can derive the partial rho partial T is equal to H rho PB. And that is the Lavey's equation, Lavey's theorem, that we have derived such a very important equation. And you can do that after class. You can make every detailed calculations to make you really understand what every steps in this, the divergence, the calculations related, the canonical equation of motion and so on. That's very frequently used in phase space calculations. You should be familiar with that, and then you can get it. Okay? Okay, so eventually I think that we have several minutes. I want to mention one thing. That is the Hamilton-Jacobi equation. Let me see that if you still have enough time to do that. Okay, let's just do it. The S, we know that the action of the system that it is equal to the delta T1, T2, the L, Q, Q dot, and T dot. Okay, and so it is equal to partial L, partial Q, delta Q, of course, that we have done that before, Q right? That we have the summation of this dt. I just repeat what we have done last time, minus d over dt partial L partial QA dot delta QA. Yes. And we can find that that's the partial L partial QA dot delta QA from the starting point to the end point, T1 to T2, and plus d over dt partial L partial QA minus partial L partial QA delta QA dt. Yes, we have these two terms. And now let's examine these expressions. If now we take the actual physical path from this point to this point, that's T1, T2. If now the delta QA here, you take the actual path of the physically realized, the physical path, this guy should be equal to 0. Right? So now you get what you get. You get partial L partial Q A dot delta Q A T2 minus, so here is the T2 partial L partial q dot q1 delta q1 q1. This equation is very important because now we do not fix the two endpoints. We just fix the path. We say that the path is the actual physical path, but the 2 points, the endpoints, is not fixed. So now let's have discussions about the two cases. The first one is that fixed what? The T1. If you have fixed T1, you have this is equal to 0, right? So now you have the partial L, partial Q dot delta Q is equal to the delta S, right? Is equal to the delta S. And delta S is equal to partial S, partial Q, delta Q. That's for simplification, we just ignore the index here. And then what can you get? This guy is equal to P delta Q. So P is equal to this. You got? P is equal to partial S, partial Q, partial L, partial Q dot. That is the first equation that you can derive now. When you fix the starting point, you get the end point is not fixed, and then you get the momentum is equal to partial S, partial Q. And similarly, you can fix T2 and let the T1 to be flexible. And what you get? You can get that minus partial L, partial Q dot delta Q1 is delta S is equal to partial S, of course, partial Q delta Q. So what you can get is the P, it is also, this is a minus P 1 delta Q1. Okay, this is, so that is the minus P, P1 is equal to the minus partial S, partial Q1. And also you can derive another thing that's very important. That is partial S, partial T is equal to minus H Q partial S, partial Q T. This equation is the time derivative of the action. And this is the Q derivative of the action. You can find that this is the momentum is equal to the gradient of the action, and the time derivative of the action is equal to the minus Hamiltonian of the systems. So if you have a three-dimensional case, you can find that P is equal to this. So it is very similar to, you can have optical wavefront S, and its gradient is equal to the k vector, and that is the P, and also the k vector of the light path. Okay? So that has very, very good similarities. And also for the Hamilton, this is the Hamilton-Jacobi equation, and including also this. From Hamilton-Jacobi equation, you can derive something that is very, the connection between the classical and quantum mechanics, because we have the WKB theory, that is the approximation theory in quantum mechanics. The WKB has very similar solutions as the Hamilton-Jacobi equation. That is one point. And also in the optics, you can find this guy is a wave optics, and this guy is just like a particle geometric optics. You can have connection between the particle optics, geometric optics, and wave optics. Wave optics is just like quantums, and particle optics is just like the classical. So you have the connection between the classical and quantum, the geometric or the particle with the wave. So Hamilton-Jacobi equation is a connection between this two very different things. So that's a very important equation. And what I want to tell you is that Hamilton-Jacobi equation is only a very special case for the derivation using the type 1 generating function in the canonical transformation. When you choose G1 to be equal to the action S and K, the new Hamiltonian equal to 0. And then from QP, you change to a Q0, P0, or Q1, P1, that is starting point Q and starting point momentum. You got completely the same result as what I have derived just now. You see what I mean? So you got the canonical transformation. If you can grasp the canonical transformations, you can very easily derive the Hamilton-Jacobi equations. So try to derive the Hamilton-Jacobi equations in different ways, in this way and also in the canonical transformation way, okay? After class. And then you can get what you have learned today. So today we have very fruitful contents, So you have a lot of homework to do. And that's now, this class is the last class of the classical mechanics. On Wednesday, we'll review and have a survey of the vector calculus and the classical electrodynamics within 2 hours. So we have another 2 hours to finish all of the classical things and some mathematical foundations for the quantum mechanics in the future. And after this week, from next week on, we'll begin to learn some very quantum mechanical things from the Hilbert space and vector, state vector, and the state space, and so on. Okay? So that's our schedule. Now, that's all. Thank you.